All right, guys. In this video, we're going to be going over the Fairfax County Unit 3 chemistry test, or we're going through the practice Unit 3 chemistry test, okay? So, again, hopefully you've tried the Unit 3 chemistry practice first. And remember, when we say Unit 3 for this is basically chemistry up through third quarter, essentially, for on the county level. There's a lot of stuff on this practice that we haven't covered yet uh, as of April 2nd in our chemistry classes at West Springfield. Um, but we will be covering this material in class and that kind of thing. So if you're doing this before you've seen it, hopefully you went through the practice, you took your best guess, and then you saw what the correct answers were. And if you need more of an explanation, again, you'll be getting those explanations in your chemistry class. But if you are absent that day or you just weren't paying attention, then I'll be going over some of this stuff in this video. Okay, so hopefully from my explanations of some of the questions, if you didn't understand why you got something wrong when you tried this the first time, hopefully now you do after you watch this video. And then after you watch this video and you think you understand it, go ahead and give the actual assessment a try. And then if you have any questions after that, make sure you talk to your chemistry teacher or you come talk to me, send me an email or something, and let me know what specific questions that you have, and I can try to answer them for you. All right. So again, we're going over the Fairfax County Unit 3 chemistry practice. Okay, so we'll get that started and go over everything question by question. All right, so here we go. All right. So again, we'll be covering these in class, and you might have seen these back in, I think, Unit 2. Maybe you've seen these. Maybe your teacher presented them to you, maybe not. It's okay. We will cover it before the SOL, but these are called potential energy diagrams. Sometimes they're called reaction coordination diagrams. And it usually says potential energy here. Maybe, this one is measured in kilocalories. Calories is just a unit of energy, just like joules is a unit of energy, or kilojoules. So it could be kilojoules over here. It could be joules. It could be kilocalories. It could be calories. Any unit of energy here. And it says potential energy, but what you want to really think of this is enthalpy, H, right? So when you see that H sign, you can think of it as heat, even though H is technically enthalpy and delta H is change in enthalpy, but you can think of it as change in heat. But again, that symbol H really doesn't mean heat, it means enthalpy, but enthalpy and heat are really the same thing as long as pressure is held constant. And so if you see H, you can think heat, but the real term is enthalpy. So when you see that word enthalpy, if it's confusing you, just replace it with heat. So delta H is the change in enthalpy of a reaction. And I think I might have it in my notes, right? So, right, delta H is the enthalpy change of a reaction, but you can think of it as the heat change of a reaction. And understand, if you see a negative energy value, that means energy is released. Okay. If you see a positive delta H, that means energy is overall absorbed. Okay. Now, the way you should think about these energy diagrams is they're the different stages of a chemical equation, of a chemical reaction. So the starting stage are the reactants, okay, and the final stage are the products. And what we have in the middle here at the top of the hump is what we call either the activated complex or the transition state of the reaction. So think you have two reactants, right? So these are the reactants, and then those are the products, okay? But before, as they collide with each other and then become the products, that kind of jumbled up mess of stuff is the high energy activated complex. And then it restabilizes in the form of the products. Okay, so you should be able to read an energy diagram like this from left to right or right to left. It really depends on what reaction are you focusing on, right? If you have a reversible reaction, you could be, if you read it left to right, if you read it this way, the start would be the reactants and the end would be the products. But you can also read it right to left, and that would be the reverse reaction. And so for the reverse reaction, this would be the starting point. So the products of the forward reaction are the reactants of the reverse reaction. And the reactants over here of the forward reaction would be the products of the reverse reaction. So going this way, we're talking about the reaction from start to finish, okay, of the forward reaction. But going this way, we're talking about the reverse reaction from start to finish, and this would be the start of the reverse reaction, and this would be the finish of the reverse reaction, okay? So before we even read the question, if I look at it, the reactants had an energy of 20 and the products have an energy of 40. So as the reaction proceeded, overall energy was absorbed, okay? From here to here, energy was absorbed. So that's telling us the forward reaction is endothermic, because overall the products are a higher enthalpy than the reactants. So the delta H was positive, okay? But if we talk about the reverse reaction, this is the start of the reverse reaction. And the reverse reaction, the reactants started at 40 kilocalories, and then the products finished for the reverse reaction at 20. So going this way, energy gets released. Energy gets lost to the surroundings, from the system to the surroundings. So going this way, energy is released. So the reverse reaction is exothermic. In this case, the forward reaction is endothermic, okay? But the change in energy of the overall process is always final minus initial. So the forward reaction, if you do final minus initial, you get a positive 20 calories. But if we talk about the reverse reaction, this would be the final part, and it would be 20 minus 40, and you get a negative 20 for your delta H, a negative 20. That much energy is released going this way, that much energy is absorbed going that way, okay? Now, another thing you can calculate from these potential energy diagrams is what we call the activation energy of the reaction. And that's the difference in energy from the starting point to the transition state. So for the forward reaction, this energy difference right here, if you follow the cursor, right, from 20 to 80, that energy is called the activation energy. So going this way, the forward reaction, the activation energy of the forward reaction is 80 minus 20. So the activation energy of the forward reaction is 60 calories, or kilocalories, but the activation of the reverse reaction would be this energy difference from this energy, the reactants of the reverse reaction, to the top of the hill, okay? And so the activation energy of the forward reaction is 60, and the activation energy of the reverse reaction is 80 minus 40, so it would be 40 going this way. So the activation energy going this way is 40, the activation energy going this way is 60, okay? But the delta H for the forward and the reverse reaction are the same number, but what matters, is it positive or is it negative? If it's positive, it's endothermic. If it's negative, it's exothermic. So notice this question is talking about the reverse reaction. So we should be reading this chart from right to left. If they just said the reaction, we can assume it's the forward reaction, or they might say the forward reaction, so we would read it left to right. But this, because they're telling us it's the reverse reaction, we got to read it from right to left, okay? All right. So again, this top of the hill is the activated complex. That's not the answer. The reverse reaction, we know right away it's exothermic. So we can cancel out that choice, I think, right? Hold on. Let me unselect this. Sorry. Maybe, can I? All right. Yeah. All right. So we know it's exothermic, so we know that's not the right answer, and we know that's the right answer. Okay. And so is it exothermic because the reactants have more energy than the products? Well, that's not true. The reactants, um, uh, oh, this has two correct answers. I think I have to fix this. So it's exothermic because the reactants have more energy than the products. That's true. So I messed this up. I'll fix it. So that's true, but also it's exothermic because the enthalpy change is negative. Okay, so I just have two possible correct answers here. So that is a correct answer, and that is a correct answer. But hopefully I've fixed this mistake, and I'm probably going to go with this one as the correct answer, and I'll change the wording of this one to make it incorrect. But yes, the reactants have higher energy than the products. And yes, that means final minus initial, products minus reactants, delta H comes out to be negative. Okay. So what do I have? I have it there too, but it's just because I didn't change the wording of this question. So again, on my paper here, choice A would be a correct statement as well. Okay. But hopefully that helps you understand these diagrams a little bit. And that's really kind of all you have to ask or have to be able to answer. When you see a diagram like this, is delta H negative or is it positive? And remember, you can be talking about the forward or the reverse reaction. And if the forward reaction is positive, delta H, the reverse reaction is negative or vice versa. Okay. The activation energies of the forward and the reverse reaction are never the same. It just depends on, from here to here or from here to here, which one's higher, right? Okay. All right. So we'll call that one the correct answer, and I will fix that to make it incorrect before you take the test. So we should be good. All right, let's go to the next one. All right. So again, we have the potential energy diagram. They're talking about the reverse reaction, and they're asking what is the activation energy. So since they gave us numbers that we can read here, we can actually calculate it. So again, for the reverse reaction, these are the reactants. That's the activated complex or the transition state. So that energy difference from here to here, that's the activation energy. So 80 minus 40, it would be 40 calories. Okay. If it asked for the forward reaction, it would be 80 minus 20, and it would be 60 if it was the forward reaction. Okay. We'll move to the next one. All right. So here they give us the delta H. So as soon as you get the reaction and they tell you the delta H of the reaction and it's negative, right away, you know it's exothermic. Exothermic. Okay. Now, another thing that is kind of important to understand is, and it's kind of counterintuitive because most of the time when I ask students this, they get the answer wrong. When you break bonds, that requires energy, right? Bonds are attractive forces between atoms that are holding them together. They're attracted to each other. That's what a chemical bond is, right? We have covalent bonds, we have ionic bonds, we have metallic bonds, but it's a force of attraction. To break that attraction requires energy. To pull things apart, to break the bond of things that are attracted to each other, think pulling magnets that are attracted to each other apart, you have to put in energy. Okay. So breaking bonds requires energy. It absorbs energy. But when bonds are formed, when attractions are formed, it releases energy. Okay. One way to remember that is remember the phrase axing is taxing, forming is warming. Axing, breaking bonds, requires energy. It's taxing on the body, right? Axing, right? If you're chopping wood, it requires your energy. It's taxing, right? So breaking requires energy. Forming is warming. When bonds are formed, it releases energy to the surroundings. And if you're a part of those surroundings, you would feel that energy and you would warm up, right? So forming attractions, bonds in this case, intermolecular forces, whatever, forming attractions releases energy. Breaking bonds requires energy. So what does that mean? If you have a delta H that's negative, that means more energy was released than required for this reaction to go. And if you think about it, what do you have to do to make this reaction happen? Well, these bonds over here have to break. I have to break the bond between the two oxygen atoms here. I have to break that bond, okay? And a new bonds are formed, right? Another bond between oxygen and nitrogen is formed over here. So breaking bonds requires energy. Forming the new bonds of the products releases energy. And if you see that the overall energy value is negative, that means more energy was released when the new bonds were formed versus energy required to break the bonds of the reactants. So as soon as you see a negative delta H, you know that the bonds of the products are stronger than the bonds of the reactants. Okay, so negative delta H, exothermic, bonds of products are stronger. So the bonds of the products require more energy to break than the bonds of the reactants. It's that first answer right there. All right, so, but let's just go down the list and just see what the other answers are here. Okay, so like bonds of the reactants require more energy. If the bonds of the reactants were stronger, then this delta H would be positive. So we know that's not true. Nope, we know it's exothermic, so we know it's not that true. More energy is conserved. No, a negative energy value means energy was released, not absorbed, not consumed. Consumed means absorbed, produced or released, right, means energy, more energy was released, right? Okay. Let's see, did I have any other notes on my paper here? So again, the activation energy of the reverse reaction for number 2. And then again, a negative delta H, you know, energy is produced or released, energy is a product. Products have stronger bonds when it's a negative delta H. If it was a positive delta H, reactants have stronger bonds. Okay. All right. So let's move on to the next one. Is that right? Okay. So which statement correctly describes how energy is involved in breaking and forming bonds? So we just talked about it. Axing is taxing, forming is warming. So energy is absorbed when bonds are broken and when bonds are formed? Nope. Energy is released when bonds are broken? Nope. Energy is released when bonds are broken? Nope. Energy absorbs when bonds are broken, but released when bonds are formed? Yes. Axing is taxing, forming is warming. Okay. All right. So here, it's just asking us ways to increase a chemical reaction. And so if you have solids, if you increase the surface area, so crush it up, make it smaller, that'll make a reaction go faster. What you're trying to get is more collisions, right? If you have more collisions, then more of those collisions have the right amount of energy, which is the activation energy. And the more collisions you have, the faster the reaction is going to go, right? And then, so if you make the particles move faster, how do we do that? You heat them up, right? Increase in temperature means particles move faster, right? So increasing the temperature speeds up a reaction. If you have a solid, crushing it up in, right? If you have salt and you're dissolving in water, if you break it up into smaller pieces, it'll dissolve faster, right? Same idea, okay? If you increase the amounts, so if you have like an aqueous solution, if you increase the concentration, increase the molarity, that means you have more particles. More particles means you'll have more collisions, you'll have a faster reaction, right? And then another thing you can do is add a catalyst. What does a catalyst do? It lowers the activation energy. So you might not increase the overall amount of collisions, but now you've lowered the bar, and now more of your collisions have enough energy to get over the hump, okay? So we're looking for things like that to increase the rate of reaction. And notice there's more than one correct answer here. We got to circle all. We have all the correct answers. Okay, so decreasing the temperature, no. Making smaller pieces of iron, yes. Adding a catalyst, yes. Okay, larger pieces of ions, no, it would go slower, right? That would be a decrease in surface area. Okay. All right. What is required for a chemical reaction to occur? Okay. You have to get what we call effective collisions. So there you go. All right, now what's an effective collision? An effective collision, and again, before I skip ahead, sorry. Axing is taxing, forming is warming, right? Here are the kind of the main ways to speed up a reaction, right? You could also lower the volume. That increases the pressure. If you have gases, that'll make more collisions happen. That's another one. But since we don't have any gases here, right? That's not really one to worry about. Okay. All right. So in order for a reaction to occur, the particles have to collide, but not every collision results in a reaction, right? Uh, Two things have to be true about the reaction. They have to have the right energy. They have to have the activation energy of the reaction. So they might collide, but if they don't collide strong enough, right, to break the bond of the reactants that need to be break for the thing to change, then that a collision with not enough energy is not going to result, right? So you have to have collisions. They have to have the right energy, but they also have the right orientation, right? Maybe if they collide this way, no reaction, even if they collide really hard. But if they collide this way, you'll get a reaction, right? So you're going to have a bunch of different collisions, but only the ones that hit in the right orientation are going to result in a reaction. But not only do they have to have the right orientation, they have to have the right energy. Okay. So if a collision has the right orientation with enough energy to overcome the activation energy of the reaction, that's called an effective collision. So in order for a reaction to occur, you have to have effective collisions. Okay. All right. Go to the next one. All right, so here we're just balancing this reaction, okay? And remember, in a question like this on the SOL, right, 1 isn't understood. So if you know you have a 1, you got to put it in there. But this one's just going to be 2, 2, 1. And it can be a kind of a hard one to balance, right? But like if we start clean here, let's just kind of go back and forth, right? 2 hydrogens, I'm not going to do anything with that. 2 oxygens, but over here we got 3, right? We got 2 here, but we also have 1 here on the right side of the yield sign, right? So this is kind of a tough one. We know we need more here, so maybe I'll put a 2 here. That's going to give me 4 oxygens, but it's also going to give me 4 H's. So I know I'm going to have to put a 2 here to get the 4 H's. And then what did that do for my oxygen? I got 4 on this side. I got 2 plus another 2. I got 4. So now I'm balanced. And then I just have to finish it up by putting a 1, whoops, there, okay? All right, so here we just have a stoichiometry problem. So they give us a lot of different stuff, but all that matters is that we have the balanced chemical equation, right? So all we have to do is take what we're given and convert it to moles. Well, they gave us that, right? So if we're following our steps for stoic, we got to know the recipe. Well, they gave us the recipe right here, right? It's the balanced chemical equation. 2, take what you're given and convert it to moles. Well, they already gave it to me in moles. Okay. So, and since they're asking for moles of something else, all I have to do is take my moles of KO2 and multiply it by the ratio, the coefficient ratio, the mole ratio of oxygen, because that's what I want, to KO2. So all I really have to do is take 3.75 moles of KO2 and multiply it by 3 over 4, right? So multiply it by 3 divided by 4, and that'll give me moles of oxygen. And that's it. So it's really just this times 3 divided by 4. I got my answer. All right, so let's see it set up using dimensional analysis, right? So 3 moles of KO2, according to the recipe, 3 moles of O2 produced for every 4 moles of KO2 that are consumed. Moles of KO2 cancel out. So take this number, multiply it by 3, divide it by 4, and you get your answer here, okay? All right, and we should have 3 sig figs. This ratio is exact, so those don't limit us in terms of sig figs. So 3.75 moles has 3 sig figs, so my final answer should have 3 significant figures, okay? All right, moving on here. Given the reaction, what type of reaction is this, right? That should be a very easy one, right? Especially if you have, it can't be single replacement. It can't be synthesis because you have 2 things being produced. It can't be decomposition because you have 2 things on this side of the arrow. So it can't be synthesis, it can't be decomposition, it can't be single replacement. It's not combustion, obviously, because it's not burning in oxygen. So what does that leave us? Double replacement, right? 2 ionic compounds, right? Sodium's replacing iron, iron's replacing sodium, right? Iron's paired up with chloride, and sodium's paired up with nitrate. It's not balanced, but that doesn't matter. It's a double replacement reaction, okay? All right, we'll go here. So we have to predict the product of this reaction, okay? I think for the SOL, the only type of reactions you have to predict are single replacements and maybe acid-base neutralization, maybe. But and it might be double replacement. All right. Combustion's easy. It's just CO2 and water, right? So it's a single replacement reaction. And what we have to remember about this is what replaces what, right? So we have lithium by itself. It's got to replace one of these things. It's got to replace H or Cl. Okay. What we need to remember from our predicting the products unit is that like replaces like. Metals replace metals or hydrogen. Non-metals replace non-metals. Halogens replace halogens. So if this was maybe fluorine instead of lithium, then it would replace chlorine. Okay. But since this is a metal will replace another metal, but it can also replace hydrogen in an acid, which HCl is an acid. It can also replace hydrogen in water. Okay. So you're going to get lithium paired up with chloride because lithium is going to replace hydrogen, and then you're going to get elemental hydrogen. Okay. So it's not going to be this. A lot of people might choose this and think it's a synthesis reaction. That's not what you should be thinking. When you have an element in a compound, you should be thinking single replacement. And the element that's by itself on this side is going to replace one of the elements in the compound on this side. Okay. Now, what is it going to replace? So your real two possibilities would be this one, okay, or this one. Okay. Well, remember, hydrogen a lot of times acts like a cation, a positive ion, right? You should think of HCl, especially when it's in water, as not being HCl, the molecule, but as separating into H plus ions and Cl minus ions. So metals become positive ions. So like replaces like. So it's going to be lithium replaces the hydrogen, kicks out the hydrogen, and you're going to get lithium chloride. Lithium chloride would be a 1-to-1 ratio because lithium is +1 and chloride's 1 minus. And then you get elemental hydrogen, which hydrogen is diatomic, so that's why it's H2 and not H. Okay. All right. 2 moles of water can be decomposed into 2 moles of hydrogen gas and 1 mole of oxygen gas, and we have to show the equation that is like, so basically here's the word equation and we have to write the chemical equation. All right. So it's a decomposition reaction, so we can cancel out that. That's a synthesis reaction. That's also a synthesis reaction. And then this just comes down to, do you remember, whoops, that's not what I want to do. Let's turn that off. Do you remember that hydrogen and oxygen are diatomic elements? So some students are going to forget that and say H plus O. You got to remember it's H2 plus O2. Okay. Which of the following explains why equations need to be balanced? Law of conservation of mass or matter. Okay. So here we have another stoichiometry problem, but it's an easy one. It's just moles to moles. So as long as we have our balanced equation, all we have to do is take 3 moles of benzene. And since we're looking for oxygen, take the 3 moles of benzene and multiply it by the oxygen to benzene mole ratio that we find in the chemical equation. So all we have to do is take the 3 moles of benzene, multiply it by 15, and then divide it by 2. And that'll be our answer. Okay, because the mole ratio of oxygen to benzene is 15 moles of oxygen for every 2 moles of benzene. Okay. So again, it's going to look very similar to this setup here. I got to find it. Okay. Sorry. All right. So now some of you might have forgotten that benzene was C6H6. Hopefully you, by process of elimination, you know that this is not benzene, and you know that this is not called benzene, and you know that this is not called benzene. So hopefully you could figure it out, right? C6H6. All right. So we'll take our 3 moles of C6H6, multiply it by 15 over 2, 15 to 2. That'll cancel out moles of benzene and give us moles of oxygen. So 3 times 15 divided by 2 will give us our answer. Okay. So that can have to be that one. All right. Move on to the next one. All right. Student is heating 10 grams of compound in an open container. Okay, so that means gas can escape. Okay, a chemical reaction occurs. The mass of the sample was measured again and found there was less. So we lost some of the matter. Oh no, where did it go? It must have escaped out of the top of the container as a gas. So this is just saying, hey, one of the products must have been a gas. Okay. All right, it's asking in this one, which of these would be a chemical reaction? Okay, so understand, like, in a chemical reaction, you can't get new elements, right? So if you have a carbon atom on the left side, you got to have a carbon atom on the right side, right? If you have oxygen, you got to have oxygen, but you can't have oxygen on one side and then all of a sudden have iron on the other side and it turn into a different element. Now, elements can turn into other elements through nuclear reactions, nuclear decay, right? Uranium-235 can turn into thorium-232 or whatever, right? But that's a nuclear reaction. We're talking chemical reactions, right? So if I have a black sphere on this side, I got to have a black sphere on this side. If I have a white sphere on this side, I got to have a white sphere on this side, right? So we know this can't be a chemical reaction. If any, I mean, it would have to be like a nuclear reaction, right? This could be, right? We have a diatomic element, and now we have a diatomic molecule, So that's a chemical reaction, okay? This one's not, right? It's just, we got the same thing on this side, we got the same thing on this side. No chemical change has occurred. And then again, this one, we have, you know, let's call it oxygen and hydrogen on this side, and then all of a sudden we got nitrogen. That's not chemical. That's would be a nucleus change, right? Nuclear, right? So it's just that one, right? And I guess you could call this a double replacement reaction, right? Okay. All right, so this one's just calculating molarity. And again, very important, you don't get a formula sheet. You got to remember molarity is moles divided by liters, right? And so that makes it easy as long as you remember that, right? They gave us moles, but they gave us milliliters. So we got to be able to convert that to liters, and then moles divided by liters will give us molarity. And that's all we have to do, okay? So here we go. All right, so I just had to divide this by 1,000 or move the decimal place to the left 3 times. So instead of 670 milliliters, I got to divide by 0.67 liters. All right, and so 1.2 divided by 0.67 comes out to be that 0.0018. And the units for molarity, you could write capital M, right? Or you could write moles per liter, right? Moles/liters. Okay, same thing, right? Right, but be careful, you know, I'm sure, you know, maybe not on this one, but I'm sure on the SOL, they'll have a question like this, and one of the answers is if you accidentally do moles divided by milliliters instead, and that number is going to pop up in your calculator, and you're going to see that answer. It's just going to be one of those trick, you know, answers, right? Or if they give you grams, you got to know to convert grams to moles before you divide by liters to make it a molarity. It's not grams per liter, that kind of thing. All right. All right, here we got another solubility curve, and we want to know what will cause the solubility of NH3 to increase. So it's kind of small font. We got to find where NH3 is here, and if we look at it, it's showing that that NH3 is becoming less soluble as temperature increases, and that's usually true for gases. Gases are less soluble in warmer water, but solids like salts, and notice like all these are salts here, their solubility kind of increases as temperature increases. You can dissolve more solid in warm water than you can in cold water, but for gases, it's the other way around, okay? So since ammonia is decreasing in solubility as temperature increases, one way we could increase the solubility is by decreasing the temperature, right? So that's probably what we're looking for here, and that would be our answer choice, okay? All right, so a lab technician prepares a solution of sodium chloride by dissolving 40 grams of the salt in 100 grams of the water And this is where we got to read the chart. This is saying how many grams you can maximally dissolve in solution in 100 grams of water. So 100 grams of water, that's what's represented on the y-axis, right? And this is the temperature. So if we go to 90 degrees Celsius and 90 degrees Celsius on the chart and find sodium chloride, which is right there, okay, the maximum amount of sodium chloride we could dissolve in 100 grams of water at 90 degrees Celsius is 40 grams. So this is saying we dissolved 40 grams in 100 grams of water at 90 degrees. So we've dissolved the maximum amount of sodium chloride we can in 100 grams of water. So what does that make our solution? It makes it saturated. If it was more than 40 grams, it would be super saturated, oversaturated. And if it was less than 40 grams at 90 degrees, it would be unsaturated. We could still keep dissolving sodium chloride in our 100 grams of water if we still needed to. But once we go past 40 grams, now we're super saturated. Okay. But right now, since we're at the max, we're saturated. Okay. So this is a strong electrolyte. So that means bright light bulb. Okay. And basic solution means pH greater than 7, right? So this one's an acid, and it would be a weak electrolyte. This one is a base, and since it's bright, a strong electrolyte. So it's sodium bicarbonate, okay? If it said weak electrolyte, but a base, then it would be this guy right here, because that dim would be a weak electrolyte, and above 7 would be basic, all right? All right. Let's just go back and see if I have any notes. Solubility. Right, okay. Right, pH greater than 7, bright light bulb, right? Okay. So we go back, and the next one, all right? So hydrochloric acid, sodium hydroxide, hopefully that's an easy one, right? It's just acid-base neutralization, right? It's a double replacement reaction. So H plus is going to pair up with OH minus, you're going to get water, and then sodium will be paired up with chloride, you'll get sodium chloride, okay? Right, so if you're trying to predict what it's going to be, right, H plus pairs up with OH minus, you get HOH, which is water, okay, same thing, and then sodium chloride, okay? And when an acid and a base neutralize each other, you're always going to get water, and you're going to get an ionic compound. And then maybe that ionic compound stays dissolved because it's soluble, or maybe it precipitates out because it's insoluble, but that really doesn't matter for this question. Okay. All right, 21. So which of these 1 molar solutions would have the highest pH? So it's which one's the strongest base, basically. So you're just looking for strong base, right? And really the only strong bases you need to look out for are metallic hydroxides, so salts that have hydroxide. Okay, so like ammonia is a base, but it's not producing its own hydroxide. It's taking an H plus away from water, and that's how you're getting hydroxide in solution. So it's a weaker base. So it is a base. It's going to have a pH greater than 7, but this one would have more hydroxide in solution and thus have a higher pH. A lower POH, higher pH. Yeah. All right, so remember, you don't get this equation, okay? So, and you're going to have to calculate pH, you're going to have to calculate POH, you're going to have to know that pH plus POH equals 14. So, you know, this is an equation that I would definitely write down on my scrap sheet of paper in my memory dump before I start the test, okay? I would have pH equals negative log of hydronium molarity. I would have POH equals negative log of OH minus molarity. And I would have pH plus POH always equals 14, okay? And so they give us, remember, when you see something in brackets, it means the molarity of that thing. So it's telling us the molarity of hydronium is 1 times 10 to the negative 6, and we want to know the pH. So for hydronium, all we have to do is take the negative log of this, and that'll be the pH. And it's easy when it's in scientific notation, and this number's 1. when I take the negative log of this, the answer is going to be 6. So it's going to be a pH of 6, and then we have to remember that pH of 6 means acidic, right? Less than 7 is acidic, greater than 7 is basic. So it is 6, but be careful, right? We might be in a rush and we might select this one. And yes, the pH is 6, but it doesn't mean basic solution. It's 6, and that's an acidic solution. Okay. All right. So 6 acidic. All right. So here we're given the hydroxide concentration. Okay. So remember, if we know the hydroxide, we can't calculate the pH right away. We have to calculate the pOH, and then 14 minus that would give us the pH, because pH plus pOH always equals 14. So we're going to take the negative log of hydroxide, but that's not pH, that's pOH. Okay, and then we got to do 14 minus. Okay, so again, we're in scientific notation, so the pOH is going to end up being 2, and then 14 minus 2 would be the pH. Right? It's a base. It's a basic solution. Sodium hydroxide is a base, so it should be above 7. Okay. So I have it on my notes here, right? So we got to know how to calculate pOH. If we know the molarity of hydroxide, that's how you calculate it. Negative log of the molarity of hydroxide. That gives us the pOH. So we know the pOH is 2, and then we know that pH and pOH always add up to 14. So that means that the pOH is 2, the pH is 12. Okay. All right. Student is completes the titration by adding 22.5 milliliters of sodium hydroxide to an unknown concentration of 20 milliliters of 0.15 molar HCl. Okay. What is the molar concentration of the NaOH? Okay. So remember, when we did our acid-base titration, it was before our stoichiometry unit. So acid-base stoichiometry, remember there's a shortcut, and this is probably the easiest way to go, especially because the base has 1 OH minus and the acid has 1 H plus. So you can do molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base. The one thing we weren't given was the molarity of the base. So we plug in the volume of the base, which is the sodium hydroxide, 22.5 milliliters. The volume of the acid was 20 milliliters. The molarity of the acid was 0.15. So all we have to do is solve for the molarity of the base, and it comes out to be 0.13. Now, you can treat this like a stoichiometry problem as well. And for that, you would have to know the balanced chemical equation, right? And know that they react in a 1-to-1 ratio. 1 mole of NaOH reacts for every 1 mole of HCl. So we would take what we're given and convert it to moles. So liters times the molarity of HCl would give us moles of HCl times our mole ratio, the coefficients in our balanced equation. That'll cancel out moles of HCl and give us moles of NaOH. And then to turn moles into a molarity, we got to divide by the volume in liters. And the volume in liters of our NaOH solution was 0.0225 liters, right? 22.5 milliliters is 0.0225 liters. So moles divided by liters is molarity, and we get the same answer. Again, I would just do it this way. If you remember that, maybe write that equation, MAVA equals MVVB, on your formula sheet. Remember, the dilution equation is very similar. M1V1 equals M2V2, right? So it's kind of very similar equation. So it's something that, you can take advantage of the shortcut, but remember the SOL is not time, so it's not that big of a deal. Okay. All right, so it was that. All right, just a couple more to go. Sorry, this is such a long video. All right, so here they give us the titration curve. All right, remember the point of inflection is always the equivalence point. Notice that the pH at the equivalence point is above 7. It's at around 8.5. And whenever you're choosing an indicator, you want the indicator to change color as close to the equivalence point pH as possible, right? So this is telling us the color change and when the color change happens, right? So this indicator would change color between 4 and 5.6. So our pH is changing at, our equivalence point's at 8.5. So that wouldn't be a good indicator. That would be too high, right? That would still be too low, but this phenolphthalein falls right into the range of where our equivalence point's going to be. So phenolphthalein would be the best indicator. Okay. All right, this is just kind of like scientific method, process, what's science all about question, that kind of thing. And notice, right, we've talked about the acid-base theories, and there's three of them, but notice like NaOH follows all three of the theories. NH3 follows two of the theories, right? It's also an Arrhenius base. C6H6 follows one of the theories, okay? Um, and, from this, we have to, which statement best reflects the nature of science, okay? And, you can read it all and probably process, which one sounds the most scientific, but it's going to be scientists develop different theories based on their research, discoveries, and needs. Okay. It's not, this one where it says it rarely overlaps. This is showing how these things overlap, right? So it definitely overlaps. So that's not the right answer. We don't just use the theories that already match published works, or there wouldn't be new science, right? And then no, we can't just go with the most popular theory, right? We got to go with the one that proves correct over and over again. Okay. All right. So which of these values is most responsible for changing the boiling and freezing points of a solvent? Remember, the more concentrated it is in terms of dissolved particles, the lower the freezing point, the higher the boiling point. And so it doesn't matter the mass of the particles. It doesn't matter that. It just depends on which one do I have more dissolved solute particles in. So it's just the number of particles. So that one. Okay. And then I'm going to move my face. All right. And the next one, which of the following is a practical application of colligative properties? So remember, the colligative properties, the ones that we focus on the most, are that, right, the boiling point increases, the freezing point decreases with the number of solute particles. But remember, if those particles are ions, now the solution can conduct electricity. So a solution being able to conduct electricity, you can also call a colligative property, right? And so there is a question here, or an answer choice that sounds like it could be right, and it's this one, right? We do drink Gatorade, electrolytes, because we need electrolytes. But that's not taking advantage of the application of the electrolyte, right? So what it is this one. Why do we put salt on our sidewalk when it's going to freezing rain or something? Because we want to lower the freezing point. We don't want the water to freeze. We want it to, even if the temperature is below freezing, we want the water to stay liquid and not turn to ice so we don't slip on it, right? So it would be that one, right? I guess another answer would be like maybe adding salt to your boiling water to make it boil at a higher temperature so you can cook your pasta faster, maybe. That might be another question that, or an answer choice that shows up, and that would be an application of it. Okay. But the one that, we see every winter is that one, right? And it's just taking advantage of the fact that we know that when we add salt to water, lowers the freezing. Okay. All right, that was a long one. Sorry about that. Hopefully you're watching at, 2 times speed, so it only took you, 25 minutes instead of 50. All right. Have a great one.